Welcome to Carolina Asks the Universe podcast. Hello everyone, welcome back to Carolina Asks the Universe podcast. Today I have another amazing, beautiful, special guest, another amazing friend of mine, PhD in astronomy, working at Harvard, another postdoc here, Kaley Brauer, and I'm very happy that you accepted my invitation here to my podcast. But at first, I would love to hear not the fully beginning of your journey, but maybe like a beginning of you as a scientist, which means PhD. So what you were working on your PhD?
Yeah, so I did my PhD at MIT, and I actually, even a little bit before that, I was at Harvard once before. I did an internship here as an undergraduate researcher back in the day, and that was the first time I really got into astronomy. And so that was actually studying X-ray binary systems, so a black hole that is accreting matter from a companion star, and then through this process is actually sending off X-rays that we can observe. But since then, I have gone much more theoretical. I'm fully a theorist with computational work now. And so at MIT and also presently, I mostly work on simulations of how the first galaxies formed, how they grew over time, and the origins of our own galaxy, the Milky Way.
Beautiful. So you spent 5 years at MIT?
5.5, yeah.
5.5 years at MIT, and now you're continuing your work at formation of the galaxies.
Correct.
So let's talk about galaxies, and we can start about what is a galaxy. What does it mean? Because we know that we are in some sort of galaxy, and some scientists just study our galaxy because there's so much things happening here, but you're kind of studying something outside, right?
Yeah, so we live in a galaxy, as you said. So our galactic home is the Milky Way. And a galaxy is basically just a collection of stars and gas. They are bound together with gravity. They grow mostly by eating up other galaxies. So you get the very first ones by gas will collapse. You start to form stars. Groupings of stars over time become a galaxy, and then they keep merging, get bigger and bigger, and you get bigger and bigger galaxies. So our galaxy, the Milky Way, is a fairly large one compared to a lot of the ones throughout cosmic time. And so it has a really long history of about 13 billion years.
Did it eat some other galaxy?
It ate many galaxies. It was very hungry.
Very hungry galaxy.
Yeah, and so that's what I am most interested in, is how you can make a Milky Way, what it ate up over time to get bigger and bigger, so we understand our own origins in the universe.
So you want to understand. So in your work, you want to understand some other galaxies in order to understand our galaxy, Milky Way, a little bit more.
Absolutely. So I want to understand how the very first galaxies formed, and then I want to understand the mergers that they all underwent to, a lot of them merged into us, so I study things that are existed 13 billion years ago, back when everything was just forming in the universe. And so then the Milky Way over time ate up a lot of those things, and if we want to understand our own history, we have to understand all of that time period. And so my subfield is actually called galactic archaeology, which I always find fun because it's like space Indiana Jones.
Space Indiana Jones, wow. Okay, so you're archaeology. What does it mean? What do you mean by that?
So it means that, typically archaeology is maybe you're interested in learning about a culture in sometime in the past, and you go and you look for fossils. You find, a pot, you find some crown or gold or whatever, and you learn about what existed during that time period, because you're finding this old stuff that still exists today. And so we do the same premise, where we look for really old stuff from the beginning of the universe that still exists today. So I do theory work around really old galaxies that they formed 13 billion years ago, and then they haven't really been doing anything since. So they formed really early, now they've been hanging out, and they're these kind of fossils that are still around us. And so these are these really tiny galaxies. We've already seen 60 of them around the Milky Way today.
So where are they?
So they're everywhere in the universe, but we the ones that we have the best data on are actually orbiting within our own galaxy. So they will be eaten at some point, but they haven't been eaten yet. And so they still exist and can be seen.
Okay, so there are like some small galaxies that our huge galaxy is kind of trying to eat.
Absolutely.
So how our galaxy is attracting them to us? It's just pure gravity, and that's...
It is, yeah, it's gravity. So the structure of the whole universe it's called the cosmic web. So it's called web because they're kind of these filaments like a web that when the gas started to collapse very early in the universe, it kind of ended up in this beautiful filamentary structure. And in the densest parts of that structure, you get the biggest galaxies, and then things fall down towards those galaxies over time. So we're a pretty big galaxy. And so things are just attracted to us over time and eventually fall into us fully and get completely eaten.
Getting back for a moment for the web, you mentioned that galaxies are like they look like a web. I know when this was discovered. I don't remember the galaxy web.
Yeah, so this is a prediction that comes from, so we have observed some of it now with, so like DESI and some of the like large surveys, but it was also a prediction of just what happens with gravity if there are small fluctuations in density very early on. So like from cosmology, we have some estimates of what everything looked like really early in the universe. So this is observations of the cosmic microwave background are the most important part here. So this is this really old light that's permeating all of space, and little densities or little fluctuations in this light tell us about the fluctuations early on in the universe. And so based on what we understand from that and just what we know about gravity, you can predict that everything will kind of fall and collapse in this kind of filamentary way, and that the galaxies will grow over time.
Amazing. If you Google the galaxy web, you see this beautiful picture.
Absolutely, yeah.
So I would recommend that. It's very pretty. But this is not what you're focusing on. You're focusing on some sample of data, and you're doing models, you mentioned, right? So how does it work? Because you mentioned models, but you also use some observational data. How do you combine that?
Absolutely. So I get my initial conditions. So how I start off my simulations is actually the same data as the cosmic microwave background. So it's the same sorts of fluctuations of density. So I start with that and what we kind of expected the beginning of the universe to look like. So then I have kind of what the beginning of the universe might look like. And then I have very high resolution models. So I'm a programmer. I do computational work. And so I add a bunch of computer models models for how the gas will collapse, how gravity will pull them together, how stars will form from that, and once they formed, what they do. And so I just take all of that physics and I put it all into one really big computer program. And so this is very slow and big. So this is not something you could ever run on your laptop. I did the math once, and if you were to run one of my simulations on your laptop, it would take over 1,000 years. So you absolutely need supercomputers for this. But once you have access to supercomputers, you can just put a lot of physics into this fake universe that you've created on a computer and then just see what happens. And so that's what I do.
And just press play.
Basically just press play, yeah. And then you check on it over time. Things probably go wrong. You fix it.
What
adjust
do you mean
your
by
models.
Go wrong? They go in a weird direction, like unphysical direction?
Yeah, so I'd say so one of our simulations, we set up all the physics models, we made this little universe in a box, and then it got too hot too quickly in a way that we know can't be true because we live in the universe and we have pretty good measurements of lots of it. And so then we know something in our model is wrong, which is useful because we didn't know that, no one knew that ahead of time before you run this. And so then we varied how the first stars form. We changed their masses a little bit, and then we ran it again. And we saw how that affected our fake universe. And along the way, we learn about what our actual universe must be like.
That's so beautiful. You mentioned supercomputers. What are they? How big are they? Where are they?
Yes, so they are very big. We're actually reaching the term that people are using these days is exascale. Exa means a really big number. It means 10 to the 18. and that's how many operations it does every single second. So
Wait, you're using such a huge computer for your work?
for my work, yes.
Wow. How expensive is that?
It is quite expensive, I guess, in terms of I didn't build it.
But like even using it is expensive.
Yes,
You have to still cool it, you have to
absolutely.
fix it.
Yeah, so these are, no individual person has a computer of this power.
Are you sure?
You're right. I don't know what all the billionaires are doing out in the world, but as far as we know, they're all owned and run by governments, large universities, things like that. And so there are a few in the world. One of the ones that I use is in Texas. It's from the University of Texas. They have an incredible computing cluster. There's some wonderful ones in Germany as well, and several run by the Department of Energy. And to get access to one of these computers, you have to apply. So they don't charge you money to use it.
Oh, so it's basically like telescopes.
Basically telescopes. So you write out why you deserve to have access to this incredible amount of power. And then if they agree with you, then they give you a bunch of hours on the computer that you can do with as you desire.
Wow. Okay. Wait. You have a model. You have a model that you wrote, or you're using someone's models, and you're like adjusting the input data.
Yeah, so I built off of hydrodynamic code that already existed, and I added a bunch of my own additional models and optimizations so we could run more. And then I set them all up, and then I ran them over the course of a few months on these huge computers.
Few months.
A few months. So even with these huge computers, it will still take a few months.
Whoa.
Yeah, so these are just in terms of, so I don't output every time step of the simulation because it's way too big. But even with me not taking out all the data that I'm creating, I save like many terabytes of data. Like each simulation is like 50 terabytes, which is not crazy in the realms of some big data things, but it's a large simulation.
That's crazy. Now I'm just thinking, because so far we are not able to, because I'm working on asteroids, and so far we are not able to simulate our solar system even. And you're trying to simulate
entire universes. Little bits, not in full universes, but so my novelty is that I simulate full galaxies and the individual stars within them. So those are many scales different, because galaxies will have, the dwarf galaxies at least will have, 10 to the 8 stars within them or so. And Milky Way is even more, but I'm not quite capturing a full Milky Way evolutions right now. But if you're capturing full galaxies, so 10 to the 8 stars, and every single star within it, which is one star, that's 8 orders of magnitude that you're resolving all at once across multiple galaxies in this volume. So that's why it's so expensive.
Crazy. This is crazy to me. Coming back to science, because we just spoke with the instrument that you're working on. So do you also use observational data?
Yes. So one of the motivations for the current simulations that have this really high resolution is that my collaborators have been getting really good data of the stars in galaxies around us and the stars in our Milky Way. So it was actually getting so much data that we were getting really detailed distributions that simulations could not explain. So the simulations, because simulations are so expensive to running a fake universe takes a lot of time and effort.
A fake universe? Yeah. Oh, are you including flat Earth in the fake universe as well?
Maybe that'll be the next one. We'll see if they still give me the access to the exascale computer for that. Because we were getting such good data, we needed then better simulations that actually resolved individual stars, because we were seeing individual stars in all of these galaxies.
Yeah.
But then the simulations were kind of blurring it out because it's too expensive it used to be too expensive to resolve. So they would have one particle that represented hundreds or thousands of stars. And a lot of simulations still do this because it's still useful. But if you care about detailed distributions, you don't get it. If you aren't resolving it, you can't see that detail. So you don't see scatter, you don't see a lot of the feedback coming from those individual stars, which is really important for these small early systems. And so that was just fully missing from a lot of these simulations. So we wanted something that actually captured it. And so now we are resolving that And we already came out with a few simulations in some of our recent papers, but the ones that are currently running are the ones we will be directly comparing with the galaxies orbiting around the Milky Way today.
Coming back for a moment to the beginning of the universe, because you mentioned that many times. So you're trying to model like how the galaxies are forming, right?
Yes.
But when do you start? You start like in the beginning of universe, or do you start like later on? Because like it's kind of like a long process, right? Like there's something that we can't see still with the redshift.
So we start our models at this is going to sound like a long time, but it's not in cosmic, just a few million years after the Big Bang. So this is before the first stars ever existed. It's when the Big Bang is still very recent, so everything's still cooling and expanding, and there's nothing forming any light yet, like in terms of stars. So we're in the dark ages is when we start. And so the only insight we have into that...
So dark ages before...
Before stars.
Before stars.
So that's, in cosmology, that's what we call the dark ages, is this time before the first stars actually started forming, which was about maybe 100 million years or so after the Big Bang. Before that,
just a little bit of time.
Just a little bit of time, in terms of the universe's opinion. So the only way we can never see this. Well, first of all, we can't see it in general because there's no stars. But also, like, even JWST, which is the most impressive technological advancement we have for astronomy, it can't see back to the very first stars in galaxies. I think I remember reading someone made some proposal for how you could observe one of the first stars, and it required this absolutely huge telescope like on the moon, something that is very insane and not something we can
there
do.
is a plan to like explore moon soon, so
maybe we could toss a huge telescope on there and
Yeah.
finally see the first stars. But right now, because we can't do that, that's why galactic archaeology is useful, where we look for the old stuff that's still hung out and is around. So we can't see the first stars through that, because the first stars die quickly. We know that they had to be pretty big because cooling was inefficient, which means that you needed a lot of mass to get big and cool and finally form a star. So this is something we understand already about what the first stars had to be like, which means that they are all dead. But we can...
Dead now.
They're all dead now, yeah. So they formed really early. They,
and they were
lived fast, died young.
Gigantic. We spoke about this last week with Jenny, that like the bigger star, the fastest it burns its fuel, and the fastest it die.
Absolutely. So they're big, they're explosive. They have no metals. That's like a characteristic because heavy elements haven't formed yet. You form those in stars, and so the very first stars, they will form them, but they haven't formed it yet. And so these are just big things of hydrogen and helium. And so because we can't see them, but they were still very influential, we want to know more about them. And so that's part of my models that's very important, is making assumptions about these first stars and seeing how it affects how galaxies grow. So this is one of our recent papers, was looking at if you just change the masses of these stars, if you assume they're a little bit bigger or a little bit smaller, it turns out that really affects the growth of galaxies, because when they're bigger, they make more radiation, and this kind of fries the galaxies. It heats them up, they can't form stars as much, they don't grow as much.
So this is like your new discovery?
Yes, so this was something that we recently were showing in one of our, it's actually our most recent paper. We were showing how if they're too big, you don't get small galaxies. They also form different amounts of like carbon, for example. And so depending on how much carbon is in the stars around us, that's a clue into also how these stars how massive they had to have been very early on. So there's a lot of ways that we can indirectly learn about them.
So this is it's like summarizing it. We have a model, a very, very complex model that has crazy amount of probably factors that you take into account for that. And then like you start from like a very early universe, as you said before, stars were actually making light. So in Dark Ages.
Yes.
So you're starting literally like in the beginning of the universe, just like few hundred millions years after the
Just a few million
just
years.
a few million years
Yes.
after the technically beginning of the universe. You create some universe.
Yes.
You play run
Yes.
and see how does it like how does it look like now, for example, you compare the universe that you created in your model to the real data that and real observations that we have right now.
Absolutely. So we're basically running experiments.
So you're basically going back in time. So,
We are going back in
time
time.
travels are actually possible.
It is with a huge computer.
With a huge computer, you can come back in time, like in the knowledge sense. So like we can go back in, like we can basically see it, right?
Yeah, so we're like step by step seeing what might have happened.
Like we are not. How sure is that?
It is not sure. So that's why we do it a bunch of different ways. That's why we keep varying things, and sometimes you run something and you say that can't be correct. But because it's so uncertain, there's a lot of exploration to be done. And so that's why we have to not just stay in our fake universes. We have to look at what's around it.
I love the name fake universe. So you're running your little fake universes in these giant computers.
Yep.
Sounds crazy and very fascinating. The more I talk about other science, other things that I like comparing to what I do, I'm like thinking about doing something else, some other research. Is there something about science that that you want to discuss before we step to another topic? Is there something it's worth mentioning?
I guess I always like, because with my day-to-day, it's a lot of debugging, a lot of coding and analyzing and making plots. So it's easy to like forget the big picture stuff, which I always think is really cool. Like we are one of like 1 trillion galaxies in the observable universe, and like 13 billion years is just incomprehensible to imagine like evolution on those timescales. And so it's just really cool to think about, and like to think about how we got here, where we're going. We're actually on a collision path with our nearby galaxy.
What's her name?
Andromeda is...
Oh, yeah, Andromeda, of course.
Yeah, so we're actually... I guess we're on collision paths with other ones, but Andromeda is they're similarly sized galaxy to us, so it's meaningful when we hit it.
Yeah, exactly. So are we going to hit it earlier than the smaller galaxies that you were mentioning that are around?
No, so this will be in like 5 billion years. And I guess I'd have to check the orbits of all the smaller galaxies. Some of them might be pretty stably just going around us, not coming in anytime soon. Some of them will definitely be eaten before then. But when we actually get close to Andromeda, a lot of things are going to get messed up. Like all the orbits are going to go crazy, stuff's going to fly all over the place. So the ship name of the galaxies is Milkdromeda. Milkdromeda will be coming to a universe. Milkdromeda coming to a universe near you in 5-ish billion years. So, yeah, so that'll, by then the sun will already also be dying. A lot is going to be going on. We will not be here probably. But if humans are still around, we'll be more than doubling the number of stars nearby in our sky. And so it'd be a beautiful view.
It's so crazy that we are building bigger and bigger telescopes, and we are seeing more and more, and there's never like the limit. There's always more to discover.
Yeah.
And it's crazy to me that we created big telescopes and we have so much data that it's even hard to analyze it for us. And I also love what you mentioned that we are like, you're doing a lot of debugging, you're doing coding on your daily basis, but this is actually like the bigger picture that we are not doing science for science, we're doing the science for humankind, so we just basically want to know what is going on in our universe.
Yeah, and where we came from, where we're going, and like the biggest sense.
And one person cannot do it, we have to do it collectively.
Absolutely.
Okay, so last final topic. How is it to be a scientist, and what would you say to people who want to be a scientist, maybe?
I really love being a scientist. I think that this is fascinating, especially when you take a step back and remember what it is we're actually studying, which is just like one of the most basic questions of humanity, of where did we come from? and better understanding our own universe and just studying things that are real. Because I love my fake universes, and don't get me wrong.
But that you are creating this fake universes to understand
But
our
yeah,
real
it's
universe.
the use of them is what's really cool. Yeah, so getting to like play with all of these, you know, making up all my own little galaxies and all my little universes, and then using that to study what our own universe is like is very cool. And I feel very privileged to be able to do it. And I still can't believe it's a job. My parents can't believe it's a job.
Oh.
They're like, oh, you can, like, what do? You study galaxies and that they pay you? And I was like, yeah, I don't understand either. But it's really great. I really enjoyed it.
I feel like my parents are also still surprised that like I can do science for a living.
No, I'm surprised myself. So it's a lovely option. And I want to just say also that the most enjoyable part though is the people that I work with and the people I get to meet, because this is like a very human undertaking. Like it is cool to like make models and learn truths, I guess. But it's more exciting to share it and like talk to people and just
and talk to inspiring, passionate about their job people.
Absolutely. Yeah.
Well, listening to people with passion is so fun.
Yeah. And so that's really my favorite part, is the people that I get to work with.
Amazing. Thank you so much.
Yeah.
So again, my guest was Kaley Brauer, and I'm Karolina Dziadura. It was a podcast. We just recorded it on Harvard. See you next week.